Hi everyone, in this video I show you how to implement a CFD analysis in OpenFoam. Let's start this talk by reviewing the CFD analysis workflow. If you have read any CFD textbook, you have likely seen many flowcharts like this one here. This one illustrating the different stages of CFD analysis and the general workflow that you should follow, which starts by pre-processing, and this is where you gather all the information about the fluid flow system that you want to simulate. And tasks here include things like generating the mesh and selecting the relevant physics. And also you here specify the boundary and initial conditions for your domain. Then the processing, where you discretize the equations according to a specific scheme and specify the iterative solver parameters like tolerance and convergence criteria. Then if the convergence is achieved, you move to the post-processing stage. And if not, you go back and adjust your simulation and solve the equations again and again until you are satisfied about your results. Okay, before doing an actual analysis, let me explain something to you. OpenFoam doesn't come with a GUI by default. That means there is no buttons or text fields for interacting with the software's backend. However, in OpenFoam, all you really need is a terminal and a text editor to get things done. Let's see this together with this dummy terminal I have created for fun. It's not a true one, just for explanation point of view. For example, the block mesh command that creates the computational mesh for a specific domain. Its input data is written in a file called blockmesh.dect. And for any solver, say ICFoam solver, its parameters are written in different input files. For example, control.dect file, which controls the overall simulation settings, things like application name, start time, end time, and so on. And there are also some other files that control the solver, things like FEV schemes, FEV solvers that we will see soon. To generalize, we can say that OpenFoam has input files to store the simulation's parameters, and commands that handle the logic of the analysis itself. So how these input files are organized? OpenFoam organizes all the related simulation files into a single directory called the case directory. This directory has a descriptive name and contains three main subdirectories. First one here is system. The parameters of numerical solution are stored in files in this directory. Things like control.dect, which controls the overall settings of the simulation, FEV schemes, where you set up the numerical schemes for individual quantities, and FEV solution, you set the parameters of solution of system of linear equation for each quantity here. Second one, constant, which contains files that define physical properties of the fluid like viscosity, density, and so on. And the mesh data is generated in this one here. So when you run the blockmesh command, the mesh data will be written here in a folder. Its name is polymesh. The last one is 0. This is where we define the initial and boundary conditions of our simulation. Okay, let's move to a terminal to see this in action. I move to the run directory, and here you can copy and run tutorials from the preset cases available in OpenFoam. I'm creating a new directory just for this course. And going to the tutorials directory, and let's try an easy one. Say this one here. So let's copy it. Follow the path by dot, which means copy it in this current directory. Here you see the 3 main directories and all the files needed for the simulation. Okay, let's open the directory in this terminal as well. For instance, say you want to create the computational mesh using blockmesh command. So we should have the blockmesh dect file that contains all the information needed to create the desired mesh. This file is located in the system directory as we see here, and also should have this name, blockmesh dect. If you change it, for example, to blockmesh, the command will complain. It's saying I am searching for this file name and I can't find it. So please say the name again. So let's do that. And it's satisfied now. You can use this handy command to check your mesh. Okay, now we have the computational mesh. Next step is to set the initial and boundary conditions. And by the way, you now see the mesh data generated here. Now we move to the 0 directory, then open and modify these files. For a text editor in Linux, you can use Vim or Nano or even gedit. Some people pronounce it Getit or Jedit. Don't care, just know how to use that. And for Windows operating system, you can use an editor like Notepad or even Microsoft Word, just anyone you like. I will open it using Vim here. Let's open the pressure field. Here you see the internal field parameters where you assign the initial conditions for the internal cells, and boundary field parameter where you assign the boundary conditions. And actually, the name of the boundary here matches the name of the boundary that was created using the blockmesh command. So if you go back to the blockmesh dect, down here you see all the boundaries of the domain that we have created. You modify the values here, but I will keep it atmospheric pressure. So let's see the velocity field. You see the same thing here. To see another one, say epsilon, you see also the same format. And as you notice, the OpenFoam input files is typically a set of lists and key value pairs that are written inside a dictionary style syntax. Okay, now we have the mesh and initial and boundary conditions. So let's move to the solver. The solver for this case is SimpleFoam. So let's see its input files. Control dict, you find here many options that control the overall simulation. Things like the time discretization, start, end, and time steps, and here the control of the output files. Let's see the other input files for the solver. FEV schemes, where you assign the discretization method. I will keep the default values. I will not change the settings in this video. FEV solution, where you set the solver parameters. Things like the relaxation factor for fields, tolerance. Okay. I think I haven't navigated the constant directory. Here you see the mesh generated, and for the fluid properties, you open transport properties file. You see here the transport model and the viscosity of the fluid. And as SimpleFoam is applicable for turbulent flow, so here you see turbulence properties file. So here you specify the simulation type and or the turbulence model. Okay, what we have done till now. We have generated the mesh. Then we specify the initial and boundary conditions of our domain. Then we specify the transport properties and turbulence properties. And for the solver, we have added the overall control of the simulation, the discretization schemes, and the solver parameters. So now we go to the next stage of the CFD analysis, which is the processing stage, which is running the solver to solve our equations. Here you see the convergence is achieved. So you move to the last step of the CFD analysis, which is supposed processing, where you visualize fields of interest and do more evaluation of your results. Here you see the solution at different iteration. To export and visualize your data, you can create a new file with a specific extension, which is .foam, which can be opened by ParaView software. So you create this file by touch command, or you can use this trick here. Just write this operator and followed by the name of the file. And you can open them by this way, or just open the GUI of ParaView software and doing the regular importing file process. But I'm not doing this here. I'm just use the parafoam command, which doesn't need any pre-created files. Here you see all the fields that we have solved for. Let's expand this one for better control. And here we go. I think that is enough for today. So by the end of the video, I hope you got a clear understanding of the OpenFoam workflow. Thanks for watching and see you later.